Previously, we used the GCNConv layer as the layer that performed the graph convolution. GCNConv uses neighborhood normalization, which typically involves averaging or normalizing the features of a node's neighbors before combining them with the node's own features. And this neighborhood normalization that the GCNConv layer performs can be problematic when you're looking at graph problems, such as graph classification. This process can reduce the GNN's ability to differentiate between distinct graph structures because it treats all neighbors equally and may lose important structural information. An alternative architecture to set up the GNN model for graph classification omits neighborhood normalization completely and adds a simple skip connection to the GN layer in order to preserve central node information. With neighborhood normalization, the graph neural network may fail to capture nuanced differences between nodes' local structures, leading to reduced performances in tasks. However, the GraphConv layer omits neighborhood normalization altogether, and that's the only change I've made to this new neural network that I've set up here. On lines 8 through 11, notice that I do not use the GCNConv layer. Instead, I use the GraphConv layer. This layer skips the normalization step, thereby maintaining the raw information from the neighbors of each node, which can help preserve more detailed structural information of the graph. And it also adds a direct connection from the input features of the node to the output of the GNN layer, which helps in retaining the central node's original information while still allowing the network to learn from its neighbors. This change helps in better preserving and utilizing the central node's information and enhances the neural network's ability to distinguish between different graph structures and will likely improve the overall performance of the classification model. The rest of the code here is exactly the same. We have the 3 convolutional layers and we have the linear layer. We have the forward pass through the model where we use the convolutional layers to generate node embeddings. We have a readout layer which aggregates the node embeddings across the entire graph. And we have the final classification layer, the linear layer which categorizes our graphs. Let's go ahead and instantiate this GNN with the new architecture. I've specified hidden channels to be equal to 32 so we have fewer hidden units in our convolution layers in this graph. We'll use the same atom optimizer as before with a learning rate of 0.01, the same cross-entropy loss, and the code on lines 4 through 17 to train the model and pick the model weights with the best validation accuracy is exactly the same. We'll train for a total of 200 epochs. The training process doesn't take very long. Our dataset isn't huge, and we are using the GPU. Let's see what the best validation accuracy is and update the model's parameters with the best model. Best accuracy was 75.5, so there's no change there. But let's see how this model performs on the test data. Let's compute the best test accuracy and you can see that it's actually fallen. Now, usually for most datasets, you're likely to see an increase in accuracy here, but for this particular dataset, eliminating neighborhood normalization and using skip connections did not improve the accuracy of the model.